Okay, now let's see. The first chapter here is ARENES. So ARENES is basically the benzene. Okay? Benzene. So that's why when they say ARENES, then they straight away start with the benzene ring here. So what is benzene ring? So benzene ring is actually the structures of C6H6. Okay? C6H6. So 6 carbon. So where is it? I put a red dot on the diagram. The first one, the second one, the third one, the fourth one, the fifth one, and the sixth one. So the red dot that I showed are the carbon, and the hydrogen, you can see it in the diagram easily. There are 6 of them also. Okay, so at the meantime, you can see the orbital here. This is trigonal planar. Trigonal planar is sp2. So that means carbon over here is doing sp2. sp2 hybridization, if you know, if you still remember that, sp2. Okay, then you know carbon has 4 electrons, 4 electrons, 4 uh 4 4 valence electrons, 4 valence electrons. So I write here carbon 4 valence electrons. So 3 electrons are used to form the sp2. 1 electron is used to form the pi. The pi. This is the sigma. So 3 sigma and 1 pi. Okay, now let's see the notes here. Benzene is a symmetrical, flat hexagonal planar molecules. So benzene is C6H6. Why it is flat? Because they are using trigonal planar. Trigonal planar is a flat structures, and all these are flat structures. So at the end they form a hexagon, something like this. 1, 2, 3, 4, 5, 6. This is a hexagon. Okay, so consists of 6 carbon-carbon single bonds and remain electrons. So you have 1 remaining electron from each carbon. Each carbon contribute 1 extra electrons, and they all go into the delocalized system. So what it means by going to the delocalized system, that means they can just move around in the p orbitals here. The p orbitals is the unhybridized orbital, so they can just move around either on top or at the bottom of the hexagon shaped. Okay, now next, all carbon-carbon bonds are the same length, 0.14 nanometer, which are smaller than a single bond but greater than a double. Okay, so they give this length because they want you to know that this length is actually in between of single bond and double bond. Double bond is stronger compared to single bond. So the bond which is stronger, the bond length is shorter. So double bond is shorter than this. Single bond is longer than this. Okay, so this is in between. That means the bond strength is stronger than this, stronger than single bond, but weaker than double bond, because the bond length is in between. So the bond strength is also in between. Okay, so we need to know that. Okay. Now we move on. Each carbon forms 3 sigma bonds, sp2 hybrid. So I already mentioned 3 sigma bond. So which 3? Okay, let's say we talk about the carbon on top. 1 sigma bond is to another carbon. Another sigma bond is to the other carbon on the other side. And the third sigma bond is to the hydrogen. So 3 sigma bond. Okay, 3 sigma bond. And 1 pi bond. 1 pi bond. Okay, so 2 between carbon and carbon on either side, and 1 between carbon and hydrogen. So altogether 3 sigma bond. A p orbital from each carbon atom overlaps above and below. Overlap above and below. So which means what? Which means they're linked together. They're linked together like this. They're linked together. On top and at the bottom. Let's say at the bottom I use green color. At the bottom, they're linked together. So at the end, the 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 fourth electrons of each carbon can either move on top of the hexagonal shape following the blue color ring. So they can just move around. No need to stick to the original carbon anymore. They can just move around any way they like within the benzene ring. Or they can also move at the bottom of the hexagonal shapes. Okay, so it's either above or below of the hexagonal shape. So we call them the localized electrons. Okay, so and it's above and below based on the notes here. Forming 2 continuous loops. The first loop is the blue one on top. The second loop is the green one at the bottom. Each carbon atom donate 1 electrons into the pi bond, delocalized. That means, there are 6 carbon. 6 carbon means 6 delocalized electrons in the benzene molecule. Okay. So I just want to add something about the structures also. As you can see the side here, sometimes you can see they draw benzene with double bond like this, and sometimes they draw a ring like this. Okay, a ring like this. So which one can we draw? So actually both will be fine. And the other thing is, when we draw double bond here, here, and here, right? And if you see it carefully, yes, sometimes they draw it at different position, So sometimes the double bond is here, here, and here, but sometimes they draw it at other positions. So which one should we follow? So we have to know about that also. When we draw benzene ring, which one should we follow for the double bond? The thing is, either one will be okay, as long as you make the double bond alternate. So something like this, where you can see where I put the double bond. Okay. Then you can also pull it in different position, like here. Okay, so either one will do. And I have to explain a little bit about these structures here. So if you see the note here, the bond length is 0.14. That time, or just now, I said the bond strength is between single bond. It's stronger than single bond and weaker than double bond. So it is where we can explain it, because the structures keep changing from these structures to these structures. At one moment it's single bond. At the other particular moment it's double bond, So the single bond and double bond is like keep exchanging, So because of that, their bond strength is like between single bond and double bond. So their bond strength is like 1.5 bond, So it's something like that. Okay, because the structures keep changing from double bond to single bond. Okay? Why they keep changing? Because the electrons are freely moved, Okay? The pi electron that we mentioned just now are freely moved. So they make the bond is like between the strength of single bond and double bond. Okay, so if you don't want to draw these structures, and then drawing this is easier. Just draw a ring in the middle, showing that the electrons can just move around. Okay, Now let's move on with 6.2, properties of benzene. Clear, colorless, non-polar liquid at room temperature and pressure. Okay, so it is volatile and has a low boiling point. Okay, so one of the examples of benzene in our daily life is in the car. So in the car, right, if you park under the hot sun, so because of the sun, which heat up the dashboard, so at the end, then we have benzene that come out from the plastic. So because of that, you have to put down your window when you start your car engine, so that you don't absorb in too much of benzene, so it is poisonous. So that is one situation where you meet benzene. Okay, so next one, relatively unreactive due to strong bonding. So the bond is quite strong, 1.5, the bond strength. Okay, so burn with smoky flame. Burn with smoky flame is reasonable also because you see the carbon, the percentage of carbon is quite high, Okay, so smoky flame is hydrocarbon, After all, this is hydrocarbon. Okay, now 6.3, naming aromatic compound. Now, what is aromatic here? Aromatic is the structure with benzene ring. With benzene ring, so aromatic. Without benzene ring, we call it aliphatic. Okay? Aliphatic is no benzene ring. No benzene ring. Aromatic has benzene ring. Okay? So name with benzene or name with phenyl. So that means when we have the benzene ring there, sometimes we can use the words benzene, as in here chlorobenzene. Sometimes we can use the words phenyl like phenol, phenol. So this one methylbenzene, phenylethene. So sometimes we name it as benzene, sometimes we name it as phenyl. So of course the idea is, benzene stay at the back, right? And if you learn how we name an organic molecule, right? So for example, like okay, let's say something that is more basic, 2-methyl, let's say 2-methyl butane. Okay, so this one is the main structures, and this one is the branch. So we have this kind of idea, Whoever stay at the back is like the main structures, whoever stay in front is like the branch. So similarly, chlorobenzene, let's say for example, our first name here, chlorobenzene. Benzene is like the main structure, chloro is like the branch. So phenol comes from the word phenyl. The phenyl is like the branch, and this is OH, the OL, the alcohol, like the main structure. Phenylethene. So ethene is like the main structure, phenyl is like the branch. It's that kind of idea. And so on. Methylbenzene means you have CH3. Nitrobenzene means you have NO2 as the branch. Benzoic acid, so you have COOH as the branch. Okay. Now, the other side we have phenylethene, phenylamine, or phenylamine. So this is where you have NH2 as the main structures. Benzene ring sounds like a branch already. Phenyl ethanoate. This is phenyl. Phenyl is the benzene ring here until the O. Okay, so it is the idea of ester, where this one comes from phenol, the alcohol. You know, ester is having two components, the alcohol component and the carboxylic acid component. This is the carboxylic acid. The carboxylic acid here has two carbon. It's actually ethanoic acid. Ethanoic acid. So they join up and then they form ester. Okay, now 6.4, electrophilic substitution mechanisms. Okay, so what is electrophile again? Try to recall back. Electrophile is the species that like electrons. Okay, that like electron. Okay, so of course, benzene rings has 6 delocalized electrons. So that's why electrophile like to attack benzene. Okay, as benzene has 6 delocalized electrons, which is very attractive for electrophile. And they will substitute. So how they substitute? Imagine that benzene has 6 hydrogen at the side here. So if electrophile is coming to react with benzene, so they will kick out one of the hydrogen and electrophile will just enter to this position, for example. Okay. So an hydrogen atom on the ring can be substituted by other atoms or group. They are called electrophile. So hydrogen, move it, electrophile come to replace it. So that is substitution. So all carbon atoms identical. That means same one, same one. 6 of the carbon is just the same. This is the symmetrical structures. So hence any hydrogen atom can be substituted. So you just pick any of the hydrogen and just substitute with electrophile. So an electrophile, the symbol E positive, can attack the ring of pi electrons. Pi electron means the extra electron, which is not from the sigma bond here. Okay, so that is the pi electron. But benzene highly stable, so E electrophile must be very strong. Okay, so they already mentioned in the note here, 6.2, you can see 6.2, relatively unreactive. Benzene is not reactive, so you want it to react, you must use a very strong electrophile to make it react. Okay, now here, a positive ion can be generated by heterolytic fissions of a covalent bond. Hence, catalyst needed to generate electrophile. Okay, so that means you want to form electrophile, you need a catalyst. You need a catalyst. You need a catalyst to form electrophile. Okay, let's say example. Chlorine form a covalent bond in this way by sharing electrons. So we have a catalyst here, aluminium chloride. So aluminium chloride is making chlorine molecule break down by going through heterolytic fissions. So heterolytic fission is where, hetero means not same, homo means same, hetero means not same. So the bonding electron is split in a situation that is not fair. One chlorine will take 2 of the bonding electrons, and the other chlorine take nothing, and hence it becomes positively charged, and this is called electrophile. So electrophile is formed after heterolytic fission happens. Okay, so these Cl positive, which act as electrophile, will go and find benzene ring and then kick out the hydrogens from the benzene ring and then they replace that positions. So something like that happens. Okay, so let's move on.